Introduction. If you only had a few minutes to understand 4G LTE Advanced for mobile broadband, this is the video you need. Let us unpack the ideas that matter most. Here is what is coming up: a quick overall summary, then a section-by-section breakdown of the most important points. Overall summary. High data rates in mobile communication. High data rates. Fundamental constraints. Higher data rates within a limited bandwidth. Higher order modulation. Wider bandwidth including multi-carrier transmission. Chapter 3. Multi-carrier transmission. One way to increase the overall transmission bandwidth without suffering from increased signal corruption due to radio channel frequency selectivity is the use of so-called multi-carrier transmission. At the same time, the impact in terms of signal corruption due to radio channel frequency selectivity depends on the bandwidth of each subcarrier. 5. Extension to wider transmission bandwidth by means of multi-carrier transmission. Chapter 1: Mobile and Systems. From the first experiments with radio communication by Guglielmo Marconi in the 1890s, the road to truly mobile radio communication has been quite long. To understand the complex mobile communication systems of today, it is important to understand where they came from and how cellular systems have evolved. Mobile communication technologies are often divided into generations, with 1G being the analog mobile radio systems of the 1980s, 2G the first digital mobile systems, and 3G the first mobile systems handling broadband data. In this context, it must first be pointed out that LTE and LTE Advanced is the same technology, with the Advanced label primarily being added to highlight the relation between LTE Release 10, LTE Advanced, and ITU/IMT Advanced, as discussed later. First, the technologies and mobile systems leading up to the starting point for 3G mobile systems will be discussed. In 1947, AT&T also introduced the cellular concept of reusing radio frequencies, which became fundamental to all subsequent mobile communication systems. With the advent of digital communication during the 1980s, the opportunity to develop a second generation of mobile communication standards and systems, based on digital technology, surfaced. With the second-generation digital mobile communications came also the opportunity to provide data services over the mobile communication networks. The primary data services introduced in 2G were text messaging, short message services, SMS, and circuit-switched data services enabling email and other data applications, initially at a modest peak data rate of kbps/s. Higher data rates were introduced later in evolved 2G systems by assigning multiple time slots to a user and through modified coding schemes. Packet data over cellular systems became a reality during the second half of the 1990s, with General Packet Radio Services, GPRS, introduced in GSM and packet data also added to other cellular technologies such as the Japanese PDC standard. The success of the wireless data service iMode in Japan, which included a complete ecosystem for service delivery, charging etc., gave a very clear indication of the potential for applications over packet data in mobile systems, in spite of the fairly low data rates supported at the time. With the advent of 3G and the higher bandwidth radio interface of UTRA, Universal Terrestrial Radio Access, came possibilities for a range of new services that were only hinted at with 2G and 2.5G. The 3G radio access development is today handled in 3GPP. Work on a third-generation mobile communications started in ITU, International Telecommunication Union, in the 1980s, first under the label Future Public Land Mobile Telecommunications Systems, FPLMTS, later changed to IMT 2001. The World Administrative Radio Congress WARC 92 identified 230 MHz of spectrum for IMT 2000 on a worldwide basis. Of these 230 MHz, 260 MHz was identified as paired spectrum for FDD, frequency division duplex, and 35 MHz as unpaired spectrum for TDD, time division duplex, both for terrestrial use. At this time, when the standardization bodies were ready to put the details into the 3GPP specifications, work on 3G mobile systems had already been ongoing for some time in the international arena within the ITUR. The main IMT 2000 recommendation is ITUR M.1457-2, which identifies the IMT 2000 Radio Interface Specifications, RSPC. The recommendation contains a family of radio interfaces, all included on an equal basis. For each radio interface, M.1457 contains an overview of the radio interface, followed by a list of references to the detailed specifications. In addition to maintaining the IMT 2000 specifications, a main activity in ITUR WP5D is the work on systems beyond IMT 2000, now called IMT Advanced. ITUR first concluded studies for IMT Advanced of services and technologies, market forecasts, principles for standardization, estimation of spectrum needs, and identification of candidate frequency bands. 4. Chapter 2, Mobile and Services. The main IMT Advanced recommendation, identifying the IMT Advanced Radio Interface Specifications, is presently named ITUR, IMT.RSPEC 7, and will be completed during 2011. 3 radio interface technologies for IMT Advanced. Adequate spectrum availability and globally harmonized spectrum are identified as essential for IMT Advanced. The so-called IMT 2000 core band at 2 GHz is in this frequency range and was the first band where 3G systems were deployed. Additional spectrum was identified for IMT 2000 at later World Radio Communication conferences. For the paired spectrum, the bands for uplink, mobile transmit, and downlink, base station transmit, are identified for frequency division duplex, FDD, operation. The evolution of 3G systems into 4G is driven by the creation and development of new services for mobile devices, and is enabled by advancement of the technology available for mobile systems. There has also been an evolution of the environment in which mobile systems are deployed and operated, in terms of competition between mobile operators, challenges from other mobile technologies, and new regulation of spectrum use and market aspects of mobile systems. The rapid increase in use of the Internet to provide all kinds of services since the 1990s started at the same time as 2G and 3G mobile systems came into widespread use. A few services were already supported by the evolved 2.5G systems, but it is not until the systems are designed primarily for IP-based services that the real mobile IP revolution can take off. An interesting aspect of the migration of broadband services to mobile devices is that a mobile flavor is also added. The mobile position and the mobility and roaming capabilities do in fact create a whole new range of services tailored to the mobile environment. The main service-related design parameters for a radio interface supporting a variety of services are data rate. Many services with lower data rates such as voice services are important and still occupy a large part of a mobile network's overall capacity, but it is the higher data rate services that drive the design of the radio interface. The ever-increasing demand for higher data rates for web browsing, streaming and file transfer pushes the peak data rates for mobile systems from kbit/s for 2G to mbit/s for 3G and getting close to gbit/s for 4G. In the case of capacity shortage in a mobile system, the quality of service, QoS, for the individual end users may be degraded. The demand for new services and for higher peak bit rates and system capacity is not only met by evolution of the technology to 4G. With more spectrum coming into use for mobile broadband, there is a need to operate mobile systems in a number of different frequency bands, in spectrum allocations of different sizes and sometimes also in fragmented spectrum. The demand for new mobile services and the evolution of the radio interface to LTE have served as drivers to evolve the core network. Setting a standard for mobile communication is not a one-time job, it is an ongoing process. 3GPP TSG RAN, Radio Access Network, is the technical specification group that has developed WCDMA, its evolution HSPA, as well as LTE/LTE Advanced, and is in the forefront of the technology. RAN WG2, dealing with the Layer 2 and Layer 3 radio interface specifications. RAN WG4, dealing with the radio frequency, RF, and radio resource management, RRM, performance requirements. Chapter 3, Power and Data. With HSPA, UTRA goes beyond the definition of a 3G mobile system and also encompasses broadband mobile data. Most notable are the requirements on high data rate at the cell edge and the importance of low delay, in addition to the normal capacity and peak data rate requirements. LTE Advanced was submitted as a candidate to the ITUR in 2009 and is now included in the set of radio interface technologies announced by ITUR 6 in October 2010 to be included as a part of the IMT Advanced Radio Interface specifications. 7.3GPP time schedule for LTE Advanced in relation to ITU time schedule on IMT Advanced. As discussed in Chapter 1, one main target for the evolution of mobile communication is to provide the possibility for significantly higher end-user data rates compared to what is achievable with, for example, the first releases of the 3G standards. Although relatively complicated in the general case, for the special case of communication over a channel, for example a radio link, only impaired by additive white Gaussian noise, the channel capacity C is given by the relatively simple expression, 12, where BW is the bandwidth available for the communication, S denotes the received signal power, and N denotes the power of the white noise impairing the received signal. Already from ECN, it should be clear that the two fundamental factors limiting the achievable data rate are the available received signal power, or more generally the available signal power to noise power ratio S/N, and the available bandwidth. The received signal power can then be expressed as S equals EBR, where EB is the received energy per information bit. Furthermore, the noise power can be expressed as N equals N0BW, where N0 is the constant noise power spectral density measured in W/Hz. For a given noise power density, any increase of the information data rate then implies a similar relative increase in the minimum required signal power S equals EBR at the receiver. Thus, in the case of data rates of the same order as or larger than the communication bandwidth, any further increase of the information data rate, without a corresponding increase in the available bandwidth, implies a larger, eventually much larger, relative increase in the minimum required received signal power. One minimum required EB/N0 at the receiver as a function of bandwidth utilization. High data rates in noise-limited scenarios. From the discussion above, some basic conclusions can be drawn regarding the provisioning of higher data rates in a mobile communication system when noise is the main source of radio link impairment. A noise-limited scenario, the data rates that can be provided in such scenarios are always limited by the available received signal power or, in the general case, the received signal power to noise power ratio. At the same time, if sufficient received signal power can be made available, basically any data rate can, at least in theory, be provided within a given limited bandwidth. In the case of low bandwidth utilization, that is, as long as the radio link data rate is substantially lower than the available bandwidth, any further increase of the data rate requires approximately the same relative increase in the received signal power. This can be referred to as bandwidth limited operation as, in this case, An increase in the bandwidth will reduce the received signal power required for a certain data rate. Thus, to make efficient use of the available received signal power or, in the general case, the available signal-to-noise ratio, the transmission bandwidth should at least be of the same order as the data rates to be provided. In particular, providing data rates of the same order as or larger than the available bandwidth, that is, with a high bandwidth utilization, would require a significant cell size reduction. Another means to increase the overall received signal power for a given transmit power is the use of additional antennas at the receiver side, also known as receive antenna diversity. This will increase the received signal power and thus, once again, allow for higher data rates for a given transmitter/receiver distance. However, providing higher data rates by the use of multiple transmit or receive antennas is only efficient up to a certain level, that is, as long as the data rates are power limited rather than bandwidth limited. An alternative to increasing the received signal power is to reduce the noise power, or more exactly the noise power density, at the receiver. Higher data rates in interference-limited scenarios. The discussion above assumed communication over a radio link only impaired by noise. Chapter 4: Signal and Bandwidth. In particular, the basic principles discussed above apply also to a scenario where interference is the main radio link impairment. The maximum data rate that can be achieved in a given bandwidth is limited by the available signal power to interference power ratio. Higher data rates within a limited bandwidth. Higher order modulation, as discussed in the previous section. Providing data rates larger than the available bandwidth is fundamentally inefficient in the sense that it requires disproportionately high signal-to-noise and signal-to-interference ratios at the receiver. At the same time, the bandwidth of the transmitted signal is, at least in principle, independent of the size of the modulation alphabet and mainly depends on the modulation rate, that is, the number of modulation symbols per second. Two signal constellations for A. QPSK, B. 16 QAM, C. 64 QAM. The use of higher order modulation provides the possibility for higher bandwidth utilization, that is, the possibility to provide higher data rates within a given bandwidth. Higher order modulation in combination with channel coding. Higher order modulation schemes such as 16 QAM and 64 QAM require, in themselves, a higher receiver EB/N0 for a given error rate, compared to QPSK. As an example, if a bandwidth utilization of close to 2 information bits per modulation symbol is required, QPSK modulation would allow for very limited channel coding rate close to 1. The use of rate 1/2 channel coding for 16 QAM obviously reduces the information data rate, and thus also the bandwidth utilization, to the same level as uncoded QPSK. From the discussion above, it can be concluded that, for a given signal-to-noise/interference ratio, a certain combination of modulation scheme and channel coding rate is optimal in the sense that it can deliver the highest bandwidth utilization, the highest data rate within a given bandwidth, for that signal-to-noise/interference ratio. Clearly, the probability for large peaks in the instantaneous power is higher in the case of higher order modulation. 3. Distribution of instantaneous power for different modulation schemes. Alternatively, the average transmit power must be reduced, implying a reduced range for a given data rate. Wider bandwidth, including multi-carrier transmission, as was shown in section. Transmission with a high bandwidth utilization is fundamentally power inefficient in the sense that it will require disproportionately high signal-to-noise and signal-to-interference ratios for a given data rate. Instead, to provide high data rates as efficiently as possible in terms of required signal-to-noise and signal-to-interference ratios, implying as good coverage as possible for high data rates, the transmission bandwidth should be at least of the same order as the data rates to be provided. However, A more specific technical issue related to wider band transmission is the increased corruption of the transmitted signal due to time dispersion on the radio channel. In the frequency domain, a time-dispersive channel corresponds to a non-constant channel frequency response, as illustrated in Figure 2.4b. This radio channel frequency selectivity will corrupt the frequency domain structure of the transmitted signal and lead to higher error rates for given signal-to-noise/interference ratios. Every radio channel is subject to frequency selectivity, at least to some extent. However, the extent to which the frequency selectivity impacts the radio communication depends on the bandwidth of the transmitted signal with, in general, larger impact for wider band transmission. For multipath propagation causing time dispersion and radio channel frequency selectivity. One special case of multi-carrier transmission is OFDM transmission, to be discussed in more detail in Chapter 3. One way to increase the overall transmission bandwidth, without suffering from increased signal corruption due to radio channel frequency selectivity, is the use of so-called multi-carrier transmission. By transmitting M signals in parallel over the same radio link, the overall data rate can be increased up to M times. Chapter 5, Oftman transmission. This has a somewhat negative impact on the overall bandwidth efficiency of this kind of multi-carrier transmission. As an example, consider the multi-carrier evolution of WCDMA/HSPA towards wider bandwidth. WCDMA has a modulation rate, also referred to as the WCDMA chip rate, of FCR equals chips/S. A second drawback of multi-carrier transmission is that, similar to the use of higher-order modulation, the parallel transmission of multiple carriers will lead to larger variations in the instantaneous transmit power. Thus, similar to the use of higher-order modulation, multi-carrier transmission will have a negative impact on the transmitter power amplifier efficiency, implying increased transmitter power consumption and increased power amplifier cost. For this reason, similar to the use of higher-order modulation, multi-carrier transmission is more suitable for the downlink, base station transmission, compared to the uplink, mobile terminal transmission, due to the higher importance of high power amplifier efficiency at the terminal. The main advantage with the kind of multi-carrier extension outlined in figure is that it provides a very smooth evolution, in terms of both radio equipment and spectrum, of an already existing radio access technology to wider transmission bandwidths and a corresponding possibility for higher data rates, especially for the downlink. Transmission by means of OFDM can be seen as a kind of multi-carrier transmission. As an example, the HSPA multi-carrier evolution to a 20 MHz overall transmission bandwidth consists of 4 sub-carriers, each with a bandwidth of the order of 5 MHz. In comparison, OFDM transmission may imply that several hundred subcarriers are transmitted over the same radio link to the same receiver. Spectrum for basic OFDM transmission. Tight frequency domain packing of the subcarriers with a subcarrier spacing f equals 1/2, where 2 is the per subcarrier modulation symbol time. The subcarrier spacing is thus equal to the per subcarrier modulation rate 1/Tuesday 1. An illustrative description of a basic OFDM modulator is provided in figure. In complex baseband notation, a basic OFDM signal xt, during the time interval mtut, m+1, 2 can thus be expressed as, where xk, t, is the kth modulated subcarrier with frequency fk equals kf and is the, generally complex, modulation symbol applied to the kth subcarrier during the mth OFDM symbol interval, that is, during the time interval mtut, m+1, Tuesday. OFDM transmission is thus block-based, implying that, during each OFDM symbol interval, NC modulation symbols are transmitted in parallel. The term orthogonal frequency division multiplex is due to the fact that two modulated OFDM subcarriers and are mutually orthogonal over the time interval MTU-T, m+1, 2, that is, thus, basic OFDM transmission can be seen as the modulation of a set of orthogonal functions k, t, where the physical resource in the case of OFDM transmission is often illustrated as a time-frequency grid according to figure, where each column corresponds to one OFDM symbol and each row corresponds to one OFDM subcarrier. To confirm this, consider a time-discrete, sampled, OFDM signal where it is assumed that the sampling rate fs is a multiple of the subcarrier spacing f, that is, fs equals 1/ts equals nf. As described in section, an uncorrupted OFDM signal can be demodulated without any interference between subcarriers. 8. Time dispersion and corresponding receive signal timing. Another way to explain the interference between subcarriers in the case of a time-dispersive channel is to have in mind that time dispersion on the radio channel is equivalent to a frequency-selective channel frequency response. Even if the frequency domain channel is constant over a bandwidth corresponding to the main lobe of an OFDM subcarrier and only the subcarrier side lobes are corrupted due to the radio channel frequency selectivity, the orthogonality between subcarriers will be lost with inter-subcarrier interference as a consequence. Due to the relatively large side lobes of each OFDM subcarrier, already a relatively limited amount of time dispersion or, equivalently, a relatively modest radio channel frequency selectivity may cause substantial interference between subcarriers. To deal with this problem and to make an OFDM signal truly insensitive to time dispersion on the radio channel, so-called cyclic prefix insertion is typically used in OFDM transmission. Closing. That brings us to the end of our review of 4G LTE Advanced for mobile broadband. Thank you for listening. If you found this helpful and would like more book summaries like this, please subscribe to the channel and turn on notifications so you never miss a new video. Tell me in the comments which book I should review next, and I will see you in the next one.